Okay, Assalamu alaikum.
Walaikum salam.
Section 17.3, which is sets in the complex plane. Okay. Let me open your book. Chapter 17. Sets in complex plane. Actually, I need to make some figures. So instead of making these figures, I will copy and paste them for you. So sets in the complex plane. First of all, a circle in a complex plane. A circle in a complex plane with a center, a circle with center Z0 and radius rho is the set of all points satisfying Z minus Z0 equal to rho. And Z minus Z0 is distance of Z from Z0. Distance between 2 points is Z minus Z0. Yani if Z is X plus IY and Z0 is X0 plus IY0, then Z minus Z0 is X minus X0 square plus Y minus Y0 square and square root. First we will see what is Z minus Z0 and then take its absolute. So if this distance between all those points, all points Z whose distance from a fixed point Z0 is equal to R, then it is rho, it is a set of circles. Rho is the radius and Z0 is the center. And a circular disk. This is a circular disk. A circular disk with the center at Z0 and radius rho. Center Z0 or center at Z0. And radius rho is the set of all points satisfying Z minus Z0 less or equal to rho. Okay. Then next definition is what is an open set? An open set, which is also called a neighborhood. Neighborhood of Z0 or an open disk. Or an open disk. What is this? It is it is Z minus Z0 less than rho. So this is a neighborhood with center at Z0 and radius is rho, but this is open. Any boundary is not included. Boundary is not included. We call it open set or a neighborhood of point Z0. Then next definition is what is an interior point of a set? What is an interior point of a set? So let's, in general, we have a set S. Let S be a set let S be a set of points. Of course, it is a set of points. A set of points in the complex plane. We have a set S in the complex plane. A point Z naught is said to be an interior point of the set S if we can make some neighborhood of Z naught that lies entirely inside S. If there exists some neighborhood of Z naught. Yani if we can make some open disk around Z naught, if there exists some neighborhood of Z naught that lies entirely whole inside S or within S. So here figure what is given is that, or suppose we have this set S and you take some point, masalan here, you take some point here, then you can make an open set, open disk around this point Z naught, which is totally, entirely within S. Okay. If it is, then this Z naught is called interior point of S. Okay. If we take a point, for example, here, if we take a point here, then whatever small radius you choose, the neighborhood here, the neighborhood, whatever small neighborhood you make, that will contain at least 1 point from S and 1 point outside of S. 1 point from S and 1 point outside from S. Now this point, this set, or let's say this point is called not interior point. This point is called boundary point. Boundary point. Okay. So here is.
Doctor, I have a question.
Yes.
What if I choose the radius is the point itself? Is it okay or not?
Radius should be here. Let me write it here. rho must be greater than 0, whatever small is. Maybe you can choose 10 power minus 10, but it should not be 0.
Okay.
All right?
Yes.
So if a point, then this red color point is also in S, although here, and if we choose whatever small, let me make another red point. Masalan here, it is very close to the boundary, but still, if distance of this point from the boundary, this red color, small red color point, let me, if this small red color point, I hope you are seeing this, is very close to as the boundary, very close. Any distance of this point from the boundary is 10 power minus 10. And it is very, very close to the boundary. Okay, still you can make, if this is Z naught has a distance from the boundary 10 power minus 10, still you can make a neighborhood whose radius is less than this number. Now this neighborhood, what I'm writing, Z minus Z naught less than 10 power minus 10 over 2, will be entirely inside S. So if that point is inside S, we can make a small neighborhood. How small? Very, very small. So this point, the red color point, is called a boundary point of S. When we say boundary point, if every neighborhood of Z naught contains at least one point from S and one point from outside of S, then it is called a boundary point of S. Let me see if they have also given the definition of a boundary point. Okay, maybe not, but they are giving this this is set in figures like this. Here. If you look at this figure, which I am taking from your book, now what is this set shown in blue color is the region which is defined by region or set with real part of Z, yani X, is greater than equal to 1. Now, greater or equal to 1 is figure 17.3.4, and simply greater than 1 or real of z, yani x, is greater or equal to 1. This is first one is figure 17.3.3 and the other one is figure 17.3.4. Figure 3.4 has a boundary included and 17.3.3 has no boundary included. So we say it is an open set and the other one is not an open set. So let us now write definition, a neighborhood or open set. Yeah. First of all, we have written a definition of open disk, and then interior point. Now open set. We say that a set is an open set if every point of the set is set S is called an open set if every point of S is an interior point of S. So here we say that this is interior point and this is not an interior point, or we say boundary point. It contains some point from S, some point from outside of S. So a set S is called an open set if every point of S is an interior point of S. There is no boundary. It is open. It is open. Yani whatever point we choose in S, we can find a small neighborhood of that point which is entirely inside S. Then, like here, let me show you in very large this figure 17.3.1. This point is taken very, very close to the boundary, but still we could find a very small neighborhood here. This neighborhood has some point with some area like this area, which is not inside this set S. But if we make the radius smaller than this, no, sorry, my mistake. Then the neighborhood is actually what is shown here. So still we can find a neighborhood that is entirely inside the region, inside the set S. So this is the small neighborhood. So if this happens, like I said before, that if distance of the point from the boundary is 10 power minus 100, you can find a neighborhood whose radius is 10 power minus 100 divided by 2, which is totally inside the point, inside the set S. Okay. Then there are some other figures here, sets given in your book. You just look at them. If every neighborhood of a point Z0 contains at least one point that is in the set, at least one point that is not in the set, that is called a boundary point. So let me also write this definition of boundary point, which I just explained you here. Boundary point of a set. A point a point Z0 is called a boundary point of the set S if every neighborhood when we say every neighborhood mean whatever small radius is, you can make it very, very small if you want. If every neighborhood of Z0 contain a point, neighborhood, so contains a point of S, or actually not a point, at least one point of S, contains at least one point of S and at least one point that is not in S. So, and this happens only when we have a set like shown in figure 17.3.4. Whatever small radius you choose, the neighborhood will have some point from S, at least one point, maybe more than 1 point, and at least one point, maybe more than 1 point, which are not in S, outside of S. Okay. Then we say that this point is the boundary point of. And what is the boundary of a set? Set of all boundary points of S is called the boundary of S. The collection of all points which are boundary points, that is called boundary of the set S. Like in figure 17.3.4, x equal to 1 is the boundary of the set. This is the boundary of the set. Okay, so we have this definition, boundary. And then a region is a domain in the complex plane. So what is a domain? If oh, first of all, before domain, we have another. Okay, any questions so far? Okay, so there is another definition here that is connected set. Connected set. A set, let us call it S. A set S is a set to be connected. A set S is said to be connected if any pair of 2 points can be connected, if any pair of points, masalan Z1 and Z2, can be connected by a polygonal line. Okay, what is this? Polygonal line mean set of some lines. Okay, instead of making this figure, let me show you this figure from your book. Masalan, this set is a connected set. We take 2 points. And we can make some straight lines to connect these 2 points. If this happens, then we say that this set is connected.
Doctor,
okay. Yes.
May you please give us an example of not connected set?
Okay. A disconnected set, we can have, maslan, a set which says that Z can be here or here. Z can be here or here. Then this is a disconnected set.
But they are two separated set, isn't it?
If we say that S is consist of Z such that Z minus 1 is less than 1, or Z minus, for example, 3 is less than 1. If we define a set S like this one, then this set S is a disconnected set. Or if the set, some set has a hole inside it.
Okay, thank you.
Lecture?
Yep.
But can't I take 2 points inside one of the circles? Or one of the sets, I mean.
Yes, but here is one word, if any pair of points, any. So if any mean, any not, you do not restrict yourself to one set. You can take in 2 points, one here and one there.
So all points in S should be connected in order to call it a connected set.
Connected set. This set is connected. Any all points in this set, they are connected to each other. They can be connected by a set of straight lines.
Okay.
We'll see more about this connected set, a set with a whole annulus region.
Doctor, is always a short line.
Always straight lines. Make few straight lines. Maybe lines are like this one. Make some lines, some straight lines, set of straight lines, polygonal line.
That means arcs are not allowed.
No. Set of straight lines. Okay. What is the next definition? The set of numbers satisfying real of z not equal to 4 is an open set, but it is not connected since it is not possible to join points on either side of the vertical line. So here is one example in your book. That example I just chose. The set real of z is not equal to 4 in all points in the complex plane, but not on the line. The points on either side of the line, real of z is x, so x equal to 4. So the points on x equal to 4 or the points which have real part equal to 4, they are not in the set. So there is a cut. There is a cut at x equal to 4. So if we take one point which has a real part bigger than 4 and one point which has real part less than 4, then we cannot connect them. Okay, here actually that is maybe confusing. By a polygonal line, I just forgot to complete this sentence. That lies entirely in the set. Yeah, I just forgot to mention this. But that is okay for this figure. Now, if you make, for example, if we have this complex plane, where it is here. If we have this complex plane and in this complex plane, we have a line which is this line. So here we say that this is origin, x-axis, real axis, imaginary axis, and this line is x equal to 4. So x equal to 4 line is a red line. Red line mean it is not included. Actually, I think they have not given here an option for a dotted line. So that's why I make it red line. So, and if you take a point here and you take a point here, you cannot connect these points by a polygonal line, by a set of straight lines which are entirely inside this set. And what is this set? This whole complex plane except red line. The set is whole complex plane except red line. So this is not a connected set. And later maybe we see more examples of this type of not connected set. A region, what is next definition? A region. A region is a domain. Okay, an open connected set is called a domain. So next definition. An open connected set is called a domain. Maybe domain of some function. We will see it later. So it is called a domain. So this one we will not say call it as a domain if it is not connected, although it is open. The set which I have just drawn with red line x equal to 4, this is an open set, but it is not connected. And what is figure 17.3.6? They are not drawing a boundary of this one. You see, there is no boundary. That is just the blue color. We say it is connected, and if it is open, then we say it is a domain. And what is next definition? Region. What do we say a region? A region is a domain in the complex plane with all, some, or none of its boundary points. If it contains all its boundary points, maybe some of its boundary points, or maybe none of its boundary points, then we call it is a region. Since an open set, an open connected set does not contain any of the boundary point, it is automatically a region. So for a region, it may be closed. Oh, I say the word close. Close mean if all the boundary points of a set are also points of the set, then it is closed set. Let me write first what is a region and then closed set. A region is a domain with all, some, or none. With all, some, or none of its boundary points. Any region may have some boundary points, but domain, no. Next, if a region, like I said before, if a region contains all its boundary points, then it is said to be closed, a closed set, or say closed region. If it contains no boundary point, then it is domain or open region. If it contains all its boundary points, then it is a closed region, or region is said to be closed, a region containing all its boundary points. For example, z minus 1 less or equal to 2. Less, if it is only less than 2, then this is open region, and if it is less equal to 2, then it is closed region, because it also includes the boundary. And this region has a name, closed disk. Closed disk. But the annular region that may have some boundary points and not all boundary points. Maslan, this region not open, similar to the interval, or closed region. Maslan 1 less equal to z minus something, z minus 2 less than Maslan 3. One point is 1, and this should be equal to maybe Maslan 2. Or 5. Something. It contains some of its boundary points, so it is neither open nor closed. Then we have some few questions, not many questions, in the exercise where you need to sketch the region. Exercise 17.3. The first few problems are where we need to sketch the region, then sketch the set of points in the complex plane that satisfy these inequalities. First is with the equalities, then we have with the inequalities, then we describe the set of points in the complex plane. Maslan, here first 8 questions. First 8 questions are real of z equal to 5. So real of z sketch the graph of the given equation. Real of z equal to 5 has the same graph like I draw here above, the graph of red color. So you make xy, x-axis, y-axis, then make a vertical line x equal to 5 for question number 1, and real of z is 5. And question number 2, imaginary of z is -2, and you make a horizontal line 2 unit below x-axis, which means y equal to -2. Yani collection of all points for which value of y is -2. And similarly, imaginary of z plus 3i. Z, I think it is written z bar. Z bar plus 3i is equal to 6. Imaginary of this complex number. Okay, what is this? Imaginary of x minus iy. This is z bar plus 3i. So imaginary of x minus iy plus 3i is equal to -y plus 3. This is the imaginary part of what is inside the bracket, and this is equal to 6, means y on the other side equal to -3. So make a horizontal line 3 units below x-axis, y equal to -3. Similarly, in question number 4, imaginary of z minus I, yani x plus iy minus I, this is equal to y minus 1, and real of z, yani x plus iy plus 4 minus 3i. What is the real part of this? X plus 4. So when we put them equal, we get y minus 1 equal to x plus 4 or y equal to x plus 5. So sketch this line in xy plane. That is the graph of equation given in number 4. Now, what are 5, 6, 7, 8? These are circles. But for question number 6, first you need to divide by 2. And that will give you a circle with the center at -1/2, because we have z minus z naught as equation of a circle. Z minus z naught. So to make it a minus, we will say that z naught is a -1/2 and radius is 2. Question 7 is a circle of radius 5 and center 4 minus 3i. We will make minus as a common factor. So 4 minus 3i. And similarly, -2 minus 2i is the center and radius is 2 for question number 8. So you can easily sketch their graphs. Then the next set of questions given in your book is to sketch graphs of. I'm not making graphs here. Graphs are straight line or circle, and you can do that. So I'm leaving this for you. Okay. What is this set? What are the sets here? So here they are saying sketch the graph of given equation. But now they are saying sketch the set of points in the complex plane satisfying the given inequality. Determine whether the set is a domain or not. Question number 9. Question number 9 mean x is less than -1. So this is the set of all points less than for which the x value is smaller than -1. So this set contains no boundary point and it is connected. So it is a domain. Similarly, the absolute value of real of z is greater than 2. Question number 10. So I hope you can make the graph in question number 9. It will be something here and less than -1. So let me choose a line. Say here is -1. So this is a set of all points which are here. This line is x equal to -1. So less than -1. And what is, if you want me to explain you some of this question, tell me. What is question number 10?
Circle. A disk.
10 is real of z absolute. Yani x absolute is greater than 2. This means x is greater than 2 or
greater than 2.
Less than -2.
Less than minus.
x is greater than 2 or x is less than -2. So now we will have two areas. One greater than 2, one less than 2. And they are not connected. So it is not a domain. Am I clear? Okay, yes. Like this. And then we make a real line. One is with x greater than 2 and other is with line x less than -2. So here this is x equal to -2, this is x equal to +2, and we have all these things less than this or greater than this. Okay, fine.
Doctor?
This is not connected region.
Okay, that was what I was going to ask.
Not connected. So x absolute greater than 2 or real of z greater than 2 is not a connected region. So it is not a domain. And something, for example, similarly, you can do for 11, 12, 13, 14. Let us see what is Maslan 14. Let us see what is this. -1 less equal to y less than 4. You know what is this? This is a strip. Okay, let me make in red color. Four, 1, 2, 3, 4. So let me get help from here. 4, and the other line is -1, red color line. So we are using red color as a line which is not included. It is red. So let us take it as a blue color line. So blue color is included. Red is red, not included. So here, this is the region, this vertical, this strip. So it is lower one is included, but the upper one is not included. So some points on the boundary are included, some points on the boundary are not included. It is a domain because it is connected region. It is connected horizontal strip. So this is origin, real axis and imaginary axis. Now it is the time for me to stop. And if you have any question, I'm here to answer.